two projects. In this video, we are going to explain about the project that is Mulberry leaf disease detection using CNN-based smart Android application. Before getting into the execution, first let us understand what is the project about. So, mulberry tree. It is the unsung hero of the silk world. Specifically, that is Morris alba. It's like the power source for silkworms, which are Bombyx mori. Why? Because these silkworms they eat only mulberry leaves. Nothing else they will do. And these leaves they are not just regular greens. They are packed with all the good stuff that is proteins, chlorophyll, carotenoids, everything a silkworm needs to grow strong and spin that luxurious, high quality silk. Without healthy mulberry leaves, the whole silk production process just falls apart. Here, the problem is mulberry trees are vulnerable to diseases like leaf spot and leaf rust, and they aren't just minor annoyances, they actually strip the leaves of their nutrients. So, think about if the leaves lose their quality, the silkworms can't perform at their best. Less silk, and whatever silk you get from that isn't of great quality. This is a huge headache for silk farmers who really rely entirely on these trees. So keeping mulberry trees healthy isn't just important, it is absolutely critical for the entire silk industry to thrive, that is to survive. And even though mulberry leaves are so important for silk production, figuring out when they are affected is a huge problem. Right now, people have to manually inspect the leaves for diseases. That might sound simple, but it is not. It is super time consuming, and think about it on a big farm. That's a lot of leaves to check. On top of that, it is easy for mistakes to happen. Not everyone are expert, and even if you are humans, they aren't perfect. And here the problem is they aren't any good publicly available data sets for mulberry leaves. This makes it really hard to create automated tools for disease detection. So if you want to build a system that can recognize these diseases, you're kind of stuck unless you collect your own data, which is another challenge altogether. That's why this project is so important. It is not just about detecting diseases faster, it is about creating something that is accurate, reliable, and practical enough to actually help silk farmers and the entire sericulture industry keep the production sustainable. So, the whole idea behind this project is detecting diseases in mulberry leaves smarter and faster. Instead of doing it manually, which we know they are slow and error prone, here we are using deep learning models to automate the process. So, we have taken some advanced pre trained models that are MobileNet V3, ResNet 50, and VGG19. They made even better. That is prediction, even better. How it is made better. So by adding four extra convolution layers to each, these layers helps to model dig deeper into the images, picking out important patterns and details which are super important for identifying diseases. And coming to the dataset part, so here we have taken the dataset from Kaggle repository and it has images from two regions in the Bangladesh. It is not massive. We just have 1091 images, but they are neatly sorted into three categories, whether it is healthy leaves, leaves with rust disease, and leaves with spots. And here we have evaluated all these models using accuracy, precision, recall, and FN score to evaluate which model is performing well. So this is all about the proposed system. To further improve the accuracy of this project here, as a step further, we are using some advanced deep learning pre-trained models that are NASNet Mobile and Exception, which are known for their powerful image recognition abilities. And the cool part here is we also tried an ensemble approach where we have combined Exception and NASNet Mobile. So think of it like teamwork. Each model brings out its strengths to the table and together they give better results. And this is classification part. Coming to the part of detection, we have also added detection as the extension. That means we will be spotting where the disease on the leaf. That is the extension part of detection. So here for detection, we have incorporated YOLO models. That is you only look once family of models. YOLO is amazing because it doesn't just classify an image, it can actually pinpoint where the disease is on the leaf. This makes the detection process incredibly precise and practical. And to make all of this usable for farmers, here we have built front end too. That is built using Flask framework. It is super friendly user interface and comes with a secure login, so only authorized users can access it. Farmers can upload images of mulberry leaves and the system quickly analyzes them to provide accurate disease diagnosis. This extension makes the whole setup scalable and accessible, ensuring that even those in remote areas can benefit from it. Moving to the implementation of the project, to implement this project, we have followed the steps mentioned in the flow of work. So we followed certain steps, set of steps for classification and the other set of steps for the detection part because they both are two different concepts. And this is the front end. So this is the front end part implementation. So now let's see how did we implement classification part. So first we have imported all the necessary libraries that are TensorFlow, NumPy, etc. to build and train the classification models. Then comes the exploratory data analysis part. So here we analyze the data set to understand its structure categories, that is whether healthy, rusted affected or spot affected, and image the distribution part. So here we will be loading mulberry leaf disease dataset and we will be doing exploratory data analysis. Then comes image data augmentation, where we enhance the data set by artificially increasing its size and variability, where we normalize pixel values and we apply shearing effect, and then we zoom in the images, and then we mirror the images horizontally and we resize the image to uniform shape. After that, we define the custom function to compute precision, recall, and FN score for performance evaluation. After that, the next step is defining early stopping to avoid either overfitting or underfitting. So here we introduce a mechanism to halt training. It's training if performance on validation data stops improving, avoiding overfitting or underfitting. Then comes calling the model. So here we load the modified CNN models that are MobileNet V3 small ResNet for classification purpose. And then all the models will be trained on the augmented data to identify disease categories. And we save the best performing model for future use in classifying leaf abnormalities. So this comes the classification part. Now moving on to the detection. So here, similar to classification, for detection also we will be loading required libraries which are OpenCV and YOLO specific modules. Then comes exploring the dataset. So here we load images into the workspace and then visualize images to check the quality and correctness. Then comes image processing, where we pre-process images into a blob format for YOLO models. And then we label the disease categories. After labeling, we highlight the affected areas with the bounding boxes. And we ensure compatibility with the model input, where we convert images array to the NumPy array. Then comes loading pre-trained model. So here we load the YOLO architecture layers and get specific layers for detection part. That is extracting the output layers. After that, again we do image pre-processing, that is advanced pre-processing. So here we pair images with the corresponding labels and adjust the color sizes. That means we will be converting images which are in blue, green, red format to red, green, blue, that is BGR to RGB. Then we segment areas of the interest, that is we create masks, and we resize the images, that is we ensure input dimensions match the YOLO requirement. And then comes data augmentation part, where we do randomizing, rotating, and transforming. Here it is increasing image diversity for robust detection. And then we install the packages which are required for the YOLO. And then we convert processed images into YOLO compatible formats. After that, we load the YOLO architecture tailored for detecting abnormalities, and the trained YOLO model is fed with the augment data to detect disease regions. That is, we train YOLO model on the augmented data. And then the best version of the YOLO model that performs well in detecting mulberry leaf diseases will be saved for the further usage in the detection. So this is how we have done the detection, and then comes the front end. So here in the front end, that is the part of front end, we built a user-friendly interface using a Flask framework with SQLite for user authentication, registration, and login. Then in the front end, users they can upload mulberry leaf images for the classification if they want to just classify which disease it is, or if they want to pinpoint the disease, they can use the detection part. And here in the front end, that given input will be pre-processed at the back end. It will be fed with the train model. Finally, outcome will be displayed through the front end of the application. So this is how we have implemented the project. Moving on to the algorithms used. These are the algorithms used in this project for classifying the mulberry leaf disease, whether the leaf is healthy, leaf rusted, or leaf spotted. And these three are the extension models. And for detection part, we have used all the three versions of the YOLO, different versions of the YOLO, which are YOLO V5, X6, YOLO V8, and YOLO V9. So we have used these three versions of the YOLO. And now comes the requirements. So to implement this project, we need basic requirements, which are hardware and software. Coming to hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let us execute. To execute, we are supposed to open the code folder, which contains source code files. So let us open the code folder of the project. These are the source code files in the code folder of the project. So here, these are the source code files. Now let us understand each of them. How will they be used in this project? Here in this Mulberry data folder, we have the dataset that is used to train the models. So here we have disease-free leaves. That means healthy mulberry leaves. These are the mulberry healthy leaves. Let's get back. And here in this folder, we have the mulberry leaves which are affected with the leaf rust. So these are the leaves of mulberry where leaf rust has been affected. And here in this, we have mulberry leaves where it is affected with the leaf spot disease. Let's get back. So all these three folders, I mean images which are in these three folders are split into train and validation. So images which are in the train folder will be used to train the model, and images which are in the validation folder will be used for evaluating the models on unseen data. So these three folders are, that means I mean images which are in these three folders are used for classification purpose. So we will be using these images for classifying. We will be using for training the models just for the classification purpose. Let's get back. And here in the sample folder, we have two subfolders, that is classification and detection. We will be using the images which are in this sample folder for in the front end for detecting the mulberry leaf images, mulberry leaf disease images. And here in the static folder, we have CSS, JavaScript, and Bootstrap files which are important for the visual appeal. And here in the templates folder, we have HTML pages that are used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here in the YOLO V5 folder, we have the dataset, which is split into two subfolders. One is train and the other one is valid. In train folder, we have two more subfolders, images, labels, and images. So let's open images folder. So here, all the three folders, that is mulberry leaves healthy, mulberry leaves which are having leaf spot, leaf rust, they are combined together, and we will be training the YOLO V5 model on these images. So images which are in this folder, we will be training these images on the YOLO V5 model. So total 834 images we have in this folder. So we will be using these images to train the YOLO V5 model. Let's get back. And here in the label folder, here in this label folder, we have annotations and the labels for the objects in the corresponding images. So here, these are the files which has the annotations and the object locations in the for the corresponding images. So for example, here each label file, it corresponds to an image file. So here each label file corresponds to an image file which provides object details, locations, and classes within the image. For example, the first annotation file, that is the first label file, it corresponds to the first image. It corresponds to the first image. And similarly for the second image, we have second annotation file. So these annotation files has the locations where that disease on that leaf is. It will spot the disease on that leaf. So that is why we have these label files. So for all the images, I mean, we have total 834 images, right? So for all those 834, we have 834 annotation files. And these annotation files, these label files, they follow the YOLO format. For example, let's open the first file. So here, it this line specifies the located object. I mean, it shows a detected object in the image, which is followed by object class index and bounding box coordinates. This is the location where that disease is present in that leaf. So this is the X limit, this is the Y limit, this is the width, and this is the height. Let's close this. Similarly, we have in all these files. Let's get back. So we do have same kind of annotation files and images in this valid folder also. Ac- Similar to the classification, here we use train folder to train the models and validation folder to evaluate the models. So images which are in this folder we will be using to train the YOLO V5 and evaluate the YOLO V5. This validation folder is used to evaluate. Let's get back. We do have same images in YOLO V8 and YOLO V9, but they are annotated differently because each YOLO version requires its own specific type of image annotation for training and also for testing purpose. So having separate folders helps keeping the dataset organized, ensuring that each YOLO version receives the correct annotation files it needs to function properly. So this is about the data set, and here we have app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating content to be rendered in HTML templates. And here we have model files. These are the model files which contain the algorithm information, and these will be loaded into the project code during runtime of the application. And here we have two Jupyter Notebook files which contains the combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. So here in this folder, that is here in this file, Jupyter Notebook file, we will be loading all the data sets, all the files in the Mulberry data, and we will use it for classification. That means we will be training all the models for classifying the Mulberry leaf disease. And here in this notebook file, we will be loading images which are in YOLO V5, YOLO V8, and YOLO V9, and we will be training all these three models for detecting the mulberry leaf disease. So this is about the notebook files, and this is the signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder. Now let us execute. So copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Now open the Anaconda prompt. So it is open. Give the command cd, give the space, paste the copied path, and now click on enter. Here, if you observe, current directory is changed to the code folders path. Now compile app.py file. So give the command cd, give the space, and paste the copied path. Now click on enter. Here, if you observe, current directory is changed to the code folders path. Now compile app.py file. So give the command python space app.py and now click on enter. So this command will execute Python script and perform runtime check for any syntax errors or logical issues. And after running the app.py file, Flash framework will host the application locally at the default address, which is the local host and the port, unless configured differently. So just wait for a while, it's being loaded. So this is the local host and this is the port. Now copy this local link provided by the Flash framework and paste it into any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project, which is developed using Flash framework. So this is the front end of the project. Now we need to get registered first. Click on register and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. Click on sign in. Give your username and the password. Click on login. We have logged in successfully. We are redirected to classification page of the project. So in this project, we will be doing classification and detection separately. So first, let's do the classification. Click on classification link. And here you can see a choose file button, right? We need to click on that for uploading the images. So click on choose file. Let us open the sample folder. Here we are doing classification first. So let's open the classification folder first. Now let us upload images from the first folder, that is disease-free leaves, and let's see whether the application will correctly predict it or not. That is, it will correctly classify or not. Let's open. So let us upload this image. Click on open and now upload it. So this given image, it will be pre-processed at the backend and then it will be fed with the train model. Then train model will be giving us the classification. So here we got the prediction. This is the uploaded image. So this is the image that we have uploaded just now. So here we got the prediction that there is no plant disease and disease leaves are healthy, disease-free leaves. That means this mulberry leaf is healthy. Now let's try uploading images from the same folder and let's see whether it will correctly predict it or not. Let's upload this one. Click on open and now upload it. So here we got the prediction. So this is the uploaded image and here we got the correct prediction that no plant disease and disease free leaves. That means this mulberry leaf is not affected with any kind of disease. Now let us upload one more folder, one more file. So let's upload this image. Click on open and now upload it. So here we got the prediction. This is the uploaded leaf and here we got the prediction that no plant disease, it is disease free leaves. Now let's try uploading images from the other folder. So let us upload images from leaf rust folder. So these are the images. Let's upload. So let's upload this one. Click on open and now upload it. Let's see what will be predicted. So this is the image that we have uploaded, and here we got the prediction that plant disease type is leaf rust. So this image we can observe that there is some black spots and rusty kind of thing, right? So here we can observe that it is correctly classifying that is plant disease type is leaf rust. So now let's try uploading some more images from the same folder. Let us upload this image. Click on open and now upload it. So this is the uploaded one, and here we got the prediction that plant disease type is leaf rust. So here leaf rust has been predicted. Now let's try uploading some more from the other folder. Get back, open leaf spot. So these are the images where mulberry leaves are affected with a leaf spot. So let's upload this one. Click on open and now upload it. So this is the uploaded image, and here we got the prediction that plant disease is there, and that disease is leaf spot disease. So this is the mulberry leaf which is affected with the spot. Now let's try uploading one more image. Click on choose file. And now let's upload this one. Click on open and now upload it. So this is the uploaded image, and here we got the prediction that leaf spot has been classified. It has been classified as leaf spot. Now let's try uploading some more. Click on choose file. So let's upload this image. Click on open and now upload it. So here we got the prediction. So this is the image uploaded, and here we got the prediction that plant disease type is leaf spot. Now let's do the detection. So click on detection. Click on choose file. We are supposed to upload images from the detection folder. Open the detection. Let us upload this image. Click on open. It has been loaded. Now click on upload and detect. Here we got the detection. As there is no disease, here we got the detection that disease-free leaf. That means it has drawn a bounding box around the leaf and given the probability score as 0.81 and labeled that disease-free leaves. Probability score is nothing but how accurate the detection is, how confident the detection is. Now let's get back, upload some more, click on choose file. So let's upload this image. So here we got the prediction that disease-free leaves. That is detection. So here it has drawn a green color bounding box around it and given a probability score of 0.88. Let's get back. Let us upload images with the disease. So let's upload this image. Click on open and now upload and detect. So here you can observe that leaf rust has been detected and a bounding box is drawn around it. Now let's upload some more. Click on choose file. So let's upload this image. Click on open and now upload and detect. So here wherever there is leaf rust, it is drawing a bounding box around it and giving the probability score. Let's get back. Now let us upload images from the other folder. So let us upload this image, click on open and now upload and detect. So here you can observe that wherever there is leaf spot, it has drawn a bounding box around it and given the probability score and the class label. Let's get back. Click on choose file. So now let us upload this image, click on open and now upload and detect. So here you can observe, right? Leaf spot has been detected and a bounding box is drawn around it. Get back. So here, did you understand the difference between classification and detection? So when we have uploaded images in the classification, we just know what is the disease affected by the leaf. And coming to the part of detection, so when we have uploaded images for detection, it is detecting, I mean the model is detecting where that disease on the leaf is. It is locating that disease and also specifying which kind of disease it is. It is pinpointing the location of the disease on the leaf. So this is how you need to execute. Now let's check with the graphs. Click on graph. So here we have graph for the classification. So here on x-axis we have accuracy score and on y-axis we have all the algorithm names which are trained for classification. And this is the precision score, this is the recall score, and this is FN score. And here comes the detection graphs. So this is the precision recall curve graph, and this is the FN curve graph. This is the confusion matrix, and this is the precision score comparison graph. This is the recall score, and this is mean average precision. Here on x-axis we have mean average precision score, and on y-axis we have all the YOLO models which are trained for detecting the leaf diseases. So mean average precision and recall are used to evaluate the detection models. Accuracy, precision, recall, and FN score are used to evaluate the classification models. Now click on logout. In this way, just by giving images to the application, it will detect and also classify the leaf diseases, that is mulberry leaf diseases. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.